Welcome to today's deep dive. So today we are looking at a really fascinating new research paper. It's from UC Berkeley, Rice University, and UC Davis, and it's titled "Towards Efficient and Practical GPU Multitasking in the Era of LLM."
Yeah, it's a bit of a mouthful, but the concepts inside are incredible.
Exactly. And the mission of our deep dive today is to really understand why the way we currently use computing power for AI is, well, it's fundamentally broken. And we're going to look at how a proposed operating system for GPUs is going to completely revolutionize the speed, the accessibility, and honestly, the cost of the AI tools you use every single day.
Right, because it impacts everyone.
It really does.
Yeah.
I mean, have you ever wondered why running massive AI models is so ridiculously expensive, or why sometimes your favorite AI chatbot is blazing fast and other times it just makes you wait for what feels like an eternity? What stands out to you when you think about AI computing power?
Well, I mean, it is this massive invisible engine running our modern world, right?
Yep.
And right now, that engine is essentially stuck in first gear. To understand why we are in this predicament, we really have to look at the staggering evolution of the hardware itself. Over the last decade, data center GPUs, the physical chips that actually do the math for AI, they've seen just an explosive leap in
The
capabilities.
numbers in the paper are wild.
Oh, they are. We are looking at peak compute throughput increasing by over 1,000 times. And memory capacity and bandwidth, that's increased by more than 20 times.
Wow.
For instance, if you look at the modern NVIDIA B300 GPU, it boasts an unbelievable 288 gigabytes of onboard memory.
That is a colossal amount of memory. Just for context, the device you're listening to this on probably has somewhere between 8 and 16 gigabytes. So we have these absolute monsters of computational power sitting in server racks. But the paper points out a glaring flaw in how we use them. They call it single-tasking.
Single-tasking.
Imagine you're traveling and you rent a massive 100-room luxury mansion for the night. But because of some bizarre zoning rule, you are only allowed to use one single room at a time.
That's a great way to put it.
Right. The other 99 rooms just sit there, completely empty, completely wasted. But you still had to pay for the whole estate. That is exactly how GPUs operate today.
And historically, there was a reason for that. GPUs were originally designed to take one massive task like, say, rendering a highly complex 3D video game environment and dedicate every single ounce of their hardware to finishing that one task as fast as possible.
But AI workloads have evolved, right?
Dramatically. Single models just cannot max out these massive modern GPUs anymore. The hardware grew into a skyscraper, but the software is still treating it like a single-family home.
Okay, let's unpack this. The paper highlights 3 specific reasons why this mismatch leads to incredibly low utilization. They note that in some data centers, GPU utilization for running AI inference is as low as 10%.
10%. It's a staggering waste of energy and money.
It really is. So let's look at reason number 1, diverse model sizes.
Right. So on one end of the spectrum, we have these gargantuan models with over 600 billion parameters. But on the other end, we're seeing a huge rise in smaller, highly efficient models with maybe 1 to 3 billion parameters.
And those are great at specialized tasks.
Exactly. The problem is if you load a tiny 1 billion parameter model onto a giant B300 GPU under that single tasking paradigm, it is going to use a tiny fraction of the memory and compute.
And the rest of the GPU.
It just sits idle, because the system simply will not allow any other application onto the chip.
Man. That brings us to reason number 2. How does the actual traffic, the load variability, play into this waste?
Well, AI traffic is incredibly spiky. A research study highlighted in our sources shows that inference request rates, basically the volume of people asking an AI to do something at any given moment, can spike by 3 times in a matter of minutes.
Just totally unpredictable.
Exactly. Furthermore, large language models, or LLMs, are inherently unpredictable by nature. When you ask an LLM a question, it generates the answer one word at a time.
You don't know if it's going to write a 1-sentence summary or a 5-page essay.
Precisely. And because cloud providers have to guarantee a certain quality of service, they provision their GPUs for the absolute peak traffic. So during off-peak hours, those incredibly expensive GPUs are doing a whole lot of nothing.
Which leads us to the third reason, heterogeneous workloads. The AI you interact with isn't always just one single monolithic brain anymore, is it?
Not at all. We are firmly in the era of compound AI systems. Think about a modern AI assistant. It might use one model to process your speech to text, another model to search a database, a third to generate a response, and maybe a fourth to check that response for safety.
And they all have different needs.
Right. Some of these tasks are compute-bound, meaning they need raw math power. Others are memory-bound, meaning they are just bottlenecked by moving data around the chip. If you run them one at a time, single tasking guarantees that one part of the GPU will always be bottlenecked while another part starves for work.
It's just so inefficient.
What's fascinating here is that the industry absolutely knows this is a problem, but the proposed fixes just haven't gone far enough. The researchers outlined 4 fundamental requirements for true, effective GPU multitasking.
Okay, lay them out for us.
First, it needs to achieve high utilization, actually using the whole chip. Second, it must provide performance guarantees so your critical apps don't suddenly lag when sharing the space. Third, it needs fault isolation, meaning if one task crashes, it doesn't take down the whole GPU. And fourth, it has to support large-scale deployment in massive cloud data centers.
Now, I know the tech world hasn't been completely ignoring this. I mean, we see industry workarounds with lots of technical acronyms like MIG, MPS, or fractional GPUs. Why aren't these current attempts enough to solve the problem?
It really boils down to flexibility and safety. Workarounds like MIG, which stands for multi-instance GPU, statically slice up the GPU into fixed pieces. You tell the system, this model gets exactly 1/4 of the GPU forever.
But as we just discussed, AI loads are incredibly dynamic.
Exactly. Static slices mean you still end up with wasted space inside those rigid quarters. Other workarounds like MPS or multi-process service and academic attempts at fractional GPUs tried to make this sharing more dynamic, but they almost entirely ignored memory sharing, focusing only on dividing up the compute cores.
And that's a huge oversight for AI.
Huge. But the most critical failure of all these methods, though, is the lack of fault isolation.
Right. I read about this in the source material, specifically regarding something called the shared CUDA execution context. Wait, why does one bug take down the entire chip? Aren't these systems isolated?
You would hope so, but they aren't. In almost all of these current work-sharing setups, all the different tasks running on the GPU are forced to share a single execution environment. That's the CUDA context.
Okay.
It is the equivalent of having 4 different drivers trying to steer a single car using the exact same steering wheel.
That sounds like a disaster waiting to happen.
It is. If one of the drivers makes a critical error, like if one AI task has a bug and crashes, the entire shared context collapses. Every other perfectly fine application running on that GPU gets taken down with it.
Wow.
Yeah. And in a multi-tenant cloud environment where different companies are renting space on the same hardware, one customer's buggy code taking down another customer's application is totally unacceptable.
Here's where it gets really interesting. This brings us to the core vision of the paper. To fix all of this, the researchers propose building a resource management layer that acts exactly like a computer operating system, but built specifically for GPUs.
They're long overdue.
Decades ago, our standard computer processors, our CPUs, went through this exact same awkward phase before operating systems came along to manage multiple applications seamlessly. Now, we are finally doing it for GPUs. They break this OS down into a few distinct functions. Let's start with compute multiplexing. How do we actually share the math-crunching cores of the GPU?
The paper outlines 2 main strategies: temporal sharing and spatial sharing. Temporal sharing is essentially time slicing. You give task A the entire GPU, but only for a tiny fraction of a second, then you rapidly swap to task B, then to task C, and back to task A.
But if you are rapidly swapping tasks on a single chip, won't the user notice a massive lag? I mean, it sounds slow.
You think so, but the research shows that individual computational steps, which are called kernels, for a model like Llama 3.8b, can finish executing in under 10 milliseconds.
10 milliseconds.
It is so fast the human eye could never perceive the swap. And because it's swapping tasks entirely, each task gets its own isolated environment, which is great for avoiding those crashes we just talked about.
Okay, that covers time slicing. What about spatial sharing? How do you run multiple tasks at the exact same time without them clashing?
If you want to push utilization to the absolute maximum, you use spatial sharing. The researchers propose using a tool called libsemral.
Libsemral. Got it.
A GPU is made up of dozens of individual work crews called streaming multiprocessors, or SMs. What libsemral does is operate at the driver level to effectively mask certain SMs from an application.
So it hides them.
Exactly. The application code doesn't have to change at all. The GPU OS just quietly herds it into a specific corner of the chip so another task can use the rest.
Going back to our mansion analogy, instead of locking 99 rooms, the GPUs acts like a highly efficient property manager. It lets different families move into different wings of the mansion simultaneously, and it blocks off the doors so they never even share a hallway.
That is a brilliant way to picture it. You get full utilization of the house, and nobody steps on anyone else's toes.
But computing is only half the battle. We also have to talk about memory multiplexing. If the OS is successfully sharing the compute cores, what makes sharing the memory so difficult when we are dealing with large language models?
Well, LLMs throw a giant curveball at memory management through something called KV caches. Older AI models, like image classifiers, used a very predictable amount of memory. You feed it a picture, uses a set amount of space, it gives you an answer.
That's neat.
Right. But an LLM's KV cache is essentially its short-term memory of the conversation so far. Because you never know how long a generated response will be. That cache grows dynamically and completely unpredictably. You just can't statically assign memory up front.
So how does the new GPUOS handle an application that might suddenly demand twice as much memory halfway through a task?
The researchers propose utilizing newly released CUDA virtual memory APIs. Just like a modern computer OS, it creates an illusion. The AI application is told it has all the memory it could ever want, virtual memory. But behind the scenes, the GPUOS is frantically mapping that virtual memory to actual physical memory pages on the fly, right as the application actually needs it.
But wait, if the OS is successfully creating virtual memory, why can't it just allocate it normally? What is stopping the system from managing memory the way my laptop does?
The roadblock is something the paper calls the PyTorch problem.
The PyTorch problem.
PyTorch is the underlying software framework that a massive amount of AI runs on today. By design, PyTorch is basically a dragon hoarding gold when it comes to memory.
Okay, I love that image.
It's true. It is built to grab as much GPU memory as it can, and even when an AI task finishes using that space, PyTorch doesn't give it back to the system. It keeps it in its own private cache just in case it needs it later.
So if you have an OS trying to manage memory across multiple applications, PyTorch is sitting there hiding all the empty space.
Exactly.
So how do they force a framework as foundational as PyTorch to play nice with the new operating system?
The solution is incredibly clever. They had the GPU driver secretly intercept the memory allocation API calls. They actually extend PyTorch's custom memory allocators so that they're forced to cooperate with the driver.
So PyTorch doesn't even know it's sharing.
Nope. PyTorch thinks it's doing its normal hoarding, but the driver is actually getting a real-time, semantics-aware map of exactly which pieces of memory are truly active and which are just sitting there gathering dust.
That is amazing. But what happens if the GPU actually does run out of physical memory? If you have all these models sharing space and their KV caches are growing unpredictably, eventually the hardware is going to get too full, right?
Yes, and that is where transparent memory swapping comes in. Instead of just crashing and giving you an out-of-memory error, the GPUOS detects the pressure and automatically evicts inactive memory pages.
Where does it send them?
It shuttles them over high-speed hardware connections, like NVLink or the PCIe bus, straight into your computer's normal CPU memory. And because the driver is secretly talking to PyTorch, it knows exactly which data is safe to evict without slowing down the active tasks.
So what does this all mean? We have compute sharing through time slicing and masking, we have virtual memory, and we have secret backchannel conversations to stop PyTorch from hoarding. How do you manage all this chaos, deciding who gets what at any given millisecond?
It requires incredibly smart resource coordination. The system provisions resources into two buckets, guaranteed and preemptible. Guaranteed means exactly what it sounds like. If a company paid for critical performance, that hardware is theirs.
Makes sense.
But if they aren't using all of it in a specific millisecond, the OS hands it out to other tasks as preemptible resources, meaning lower priority tasks can use it, but they have to give it back the instant the critical task needs it again.
But how does the OS decide which of the lower priority tasks actually gets those spare resources? There must be a system for that.
Yes, through something called a utility curve. Not all AI tasks benefit from more resources in the same way. The researchers mapped this out beautifully. Imagine two different tasks, kernel 1 and kernel 2. Kernel 1 has a linear utility curve. It is like adding lanes to a clear highway. Every extra bit of computing power you give it makes it run proportionally faster. Kernel 2, however, hits a wall very quickly. Maybe it's bottlenecked by how fast it can read memory, not how much math it can do.
Right, so giving it more compute power is useless.
Exactly. It's like adding lanes to a highway where the off-ramp is totally blocked. Giving it more lanes doesn't speed anything up. The utility-guided coordination policy looks at these curves and smartly gives the spare resources only to the tasks that will actually benefit from them.
And that pushes overall hardware utilization through the roof.
It really does.
Now, we talked earlier about the catastrophic crashing issue, the shared CUDA context where one bug takes down the whole chip. How does this new operating system fix the fault isolation problem?
It requires completely re-architecting the GPU driver. The key insight from the paper is meticulously tracking the hardware. When the driver launches a kernel, it records exactly which physical hardware components, which specific groups of streaming multiprocessors are assigned to that process.
Oh, I see where this is going.
Right. If a hardware fault occurs or a process crashes, the driver instantly checks that registry. It identifies exactly which hardware slice was running the buggy code, and it gracefully terminates only that specific process.
And the rest of the GPU.
Keeps humming along as if nothing happened.
That's huge.
It is. If we connect this to the bigger picture, this kind of isolation is what makes large-scale deployment possible. We aren't just talking about one GPU in a desktop. We are talking about vast cloud data centers. Most massive data centers use orchestration software called Kubernetes to manage all their applications. The problem is that, historically, Kubernetes treats a GPU as a monolithic, indivisible block.
So when Kubernetes looks at a server rack, it just sees whole numbers. It says, I have 8 GPUs here, and it has no concept of an OS slicing them into dozens of constantly shifting pieces.
Precisely. To fix this, the researchers proposed tapping into a relatively new feature called Kubernetes Dynamic Resource Allocation, or DRA. By extending DRA, they can teach these massive cloud orchestrators how to see and manage these dynamic slices.
That bridges the gap between the hardware and the cloud software.
Exactly, but it goes beyond just seeing them.
Yeah.
It's about network communication, too. In a data center, GPUs talk to each other constantly, using specialized high-speed networks like NVLink or software libraries like NCCL.
Okay.
Right now, these networks assume they're talking to a whole GPU. We have to intercept those signals and trick the network into thinking our dynamic slice of the GPU is actually an independent standalone chip.
I want to bring all of this incredibly cool, highly technical engineering back down to earth for a second. Why should you, the listener, care about the intricacies of GPU memory swapping, Kubernetes orchestration, and network interception?
Good question.
You should care, because this invisible operating system layer is the exact technology required to make AI faster, dramatically cheaper, and more accessible for everyone. Right now, companies are spending billions of dollars buying physical GPUs and wasting up to 90% of their potential power.
It's a massive drain.
It is. And that waste gets passed down to you in subscription fees, in slower apps, in delayed features. By building an OS that lets us squeeze every last drop of math out of this silicon, we prevent massive wastes of energy and capital.
This raises an important question, though, because the researchers are incredibly transparent about the open challenges that still remain. A major one is security isolation.
Security is always the catch.
It is. When you have multiple tasks sharing the exact same physical hardware, especially in a public cloud environment, where a bank might be renting space on the same chip as a random startup, you open the door to what are called side-channel attacks.
What does a side-channel attack look like in this shared environment?
Instead of trying to break into your software directly, a malicious actor monitors the physical hardware itself. They might watch the power consumption or measure exactly how quickly the shared memory cache is being accessed.
That sounds really hard to defend against.
It is. By analyzing those physical hardware fluctuations, they can potentially infer what a co-running task is doing. While the virtual memory design provides basic safety, fully locking down those side channels is a major open problem for this OS.
Are there mechanical hurdles as well? Because the paper mentions the difficulty of controlling memory bandwidth. Why is that so tricky?
Well, current GPU hardware just wasn't built to throttle memory access. You could successfully assign just 20% of the compute cores to an application, but that application could still greedily suck up 100% of the memory bandwidth, starving everything else on the chip.
Just going rogue on the memory?
Yeah. The researchers propose a fascinating, almost hacky workaround to fix this, instrumenting the memory instructions and injecting no ops.
No ops, like telling the processor to do no operation.
Yes, exactly. They artificially inject tiny delays like mathematical speed bumps into the greedy application's memory requests.
Oh, that's clever.
It forces the application to slow down and share the bandwidth. It just shows how much we're having to invent from scratch to force these single-tasking chips to operate in a multitasking world.
I want to leave you with a final thought to mull over today. If this research succeeds, and this new operating system layer perfectly virtualizes GPUs, dividing them up dynamically across massive data centers, will future software developers even need to know what a GPU is?
That's a wild thought.
For decades, developers have had to write code specifically tailored to the physical quirks of NVIDIA or AMD chips. But if this abstraction layer becomes seamless, maybe AI models will soon just flow across a global, decentralized grid of invisible compute power.
Just pure compute.
Exactly. You won't rent a GPU, you'll just tap into a universal stream of intelligence where the physical chip running the math is entirely irrelevant.
It changes everything.
It is an absolutely wild future to think about, and it is being built right now in research labs like those at Berkeley, Rice, and UC Davis. Thank you so much for joining us for this conversation. We hope you learned something new, and we will catch you on the next Deep Dive.